I believe we all love music, but have you ever imagined why some notes just sound right together? What are the patterns behind harmony? In this video, we'll explore the basic of music, the math behind it, and how both contribute to perfect melody. Let's get started. Let's start with some basic concepts. The keyboard is made out of multiple cycles, each being a repetition of notes. Each cycle contains 7 white keys, namely C, D, E, F, G, A, B, and 5 black keys lying above them, namely C sharp, D sharp, F sharp, G sharp, and A sharp. An interval is the distance between two notes. The smallest step is called a semitone, like from C to C sharp or E to F. There aren't any note in between these two notes. Two semitones make a tone, like from C to D or B to C sharp. There's one note in between them. I'll keep the keyboard here for the rest of the video. Moving on, the frequency tells us how many waves a sound completes in 1 second, measured in hertz or Hz. More vibrations means a higher frequency, therefore a higher pitch. For example, this is 2 Hz, 4 Hz, 8 Hz, and 16 Hz, representing 16 waves completed in 1 second. The frequency of C4, which is the 4C on the piano, is around 262 Hz, and the frequency of C5 is 524 Hz. Take a guess, what will be the frequency of C6? Surprisingly, it is not 524 plus 262, 786 Hz. In fact, for every octave or cycle on the piano, the frequency doubles, so C6 is actually 1048 Hz. Next are some of my understanding. In our ears, the sound sounds like a linear ascent, but actually the frequency is an exponential ascent. This is something very interesting and important. Scientist Ernst Weber discovered that the human perception is proportional to the logarithm of the physical stimulus, which basically means that as humans feel a gentle linear progression when something is actually exponentially increasing. When something is small, a small change is easy to notice. When something is big, you need a bigger change to notice it. Alright, remember that concept when we step back to music. Let's go on to scales. A scale is a consecutive series of notes between an octave with a pattern. For example, the C major scales are all the white keys, starting at C. C, D, E, F, G, A, B, C. Now here's the fun part. If you look at the intervals between consecutive notes, we can notice a pattern. Tone, tone, semitone, tone, 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 semitone. In fact, using this pattern, we can figure out all the scales. Starting the same pattern from D, and you get a D major. D, E, F sharp, G, A, B, C sharp, D. But why are intervals so important? What actually is similar harmony? Well, the C major sounds nice to our ears, and thanks to the exponential relationship between pitch, shifting scales preserve the harmony because every note shifts upward in a certain ratio. Here, from C to D, a tone is around 1.1225, making the D major sound similar to the C major, even though it's higher. But why is it 1.1225? How can we predict harmony? Now we already know that an octave means the frequency doubles. There are 12 equal semitone steps in one octave, and each step must multiply the frequency by the same ratio. So if between two semitones the ratio is R, then an octave is essentially multiplying R 12 times. We know that results into 2. So we got R to the power of 12 equals 2. Solve the equation, and we get r equals 2 to the power of a 12th. The ratio for a semitone is 2 to the power of a 12th, which estimated to 1.0594. A tone is essentially doing a semitone twice. Therefore, the ratio of frequency between a tone should be r times r, or r squared. That results into 2 to the power of 2 over 12, which is estimated to 1.1225. That's how we get the number. Now, if we look at what each value is estimated to which fraction, some intervals form a simple fraction, like 2 to the power of 4 over 12, which represents 4 semitones apart, and 2 to the power of 7 over 12, which represents 7 semitones apart. Others, like 2 to the power of 11 over 12, which is 11 semitones apart, are more complex fractions. Did you hear the math behind it? That's right, simple fractions led to more pleasant sound. Math explains why some combinations are harmonious and others are dissonant. Our brains naturally prefer simple fractions, small numbers in the numerator and denominator, because they sound smoother. Larger, more complex ratios produce tension. That's why the difference between C to E and C to B is so obvious to our ears. The math directly affects perception. From octaves to scales to harmony, music is full of mathematical inaction. Next time you listen to a song, remember, your brain decodes sounds into harmony.